Hello. Today we're going to be talking about the graphs of sine and cosine. Here on the left, we have the basic sine function. This is the graph of y equals sine x. Notice a few things that the graph continues all the way to the left and to the right, and it's infinitely long. Since sine is a function of an angle, essentially, we can put in any angle into sine, and we're going to get a value between -1 and 1. So these bottom points are -1, and our top point here is +1. So the entire graph is going to fall between -1 and 1. So this is the base version of the sine function. It starts at 0 because sine is our y on our unit circle. So if we have our unit circle, okay, our first point here, y is 0 and x is 1. So if we look at y equals cosine of x, graphed over here, we're going to start at 1. So here we started at 0, here we started at 1. But if you notice the pattern here, these waves are essentially the same. So this one goes from 0 to 1, back down to 0, to -1, and then back to 0 as we go around the unit circle. So 0, 1 at the top, back to 0, down to -1, and then back to 0. Now, since cosine is x, instead of starting at 0, we're starting at 1, but we go 1, 0, -1, 0, +1. So we get the exact same pattern, and the difference between each of these key points is going to be pi over 2, or 90 degrees. So since these are the same, the graphs look very similar. The difference between these graphs is essentially cosine is shifted version of sine. So you can write cosine using the sine function by doing a translation. And the translation would be left 90 degrees. So this point right here gets shifted left. So if we shifted it right there, then this point would be shifted 90 degrees. This point would be shifted 90 degrees, and this point would be shifted 90 degrees. And when we do that, we get the same graph as over here. +1, 0, -1, 0, and then +1 to complete the cycle. Now, these are the base versions of sine and cosine, and these can be modified in the same way that we have done translations, dilations, reflections, any of the other things we've done previously algebraically. So when we're talking about a sine function and we wanted to graph a sine function, let's say that we wanted to graph y equals 3 times the sine of x. Well, the first thing we want to do is we want to find out what happens at key features. And again, the key features are the quadrantals, because these we know should be at 0, 1, 0, -1, and then back at 0, and follow this pattern, assuming we haven't stretched out our function or anything else. So these key points in radians are going to be at 0, pi over 2, pi, 3 pi over 2, and 2 pi. So what we can do is we can plug in these points into the new function and see where the graph is. If we plug in 0 here, sine of 0 is 0. So 0 times 3 is going to be 0. So our graph would still be at 0. If we were to plug in pi over 2, at pi over 2, sine is equal to 1, and so we're going to get 1 times 3. So our graph is actually, instead of being here at 1, it's going to be at 3. And then when we plug in pi, it's going to be sine of pi is 0. So 3 times 0 is still 0. So we're back down here. And when we plug in 3 pi over 2, we're going to get -1 because the sine of 3 pi over 2 is -1 times 3 is going to be -3. So then we're going to be down here. And then finally, when we plug in 2 pi, sine of 2 pi is 0. 0 times 3 is 0. So we're back here. So now our function's going to go up here, back down here, and then back to 0. And so we've essentially stretched out the function. And if we look at a nice version of this graph, we multiply our sine function by 3, we're going to get this whole graph stretched. And again, those key features we talked about over here of 0, pi over 2, pi, 3 pi over 2, and 2 pi are all multiplied by 3. So the ones that were 0 stayed at 0, and the ones that were at 1 are now at 3. And every point in between stretches. And so when we're talking about this, we're actually talking about the amplitude. So if we wanted to look at the trig functions themselves, we typically talk about certain features, and one of which is the amplitude. So if we have y equals a times the sine of x, or y equals a times the cosine of x, this multiplier here is going to stretch the graph vertically or compress it vertically. So if our a is bigger than 1, it's going to cause it to stretch, like over here with our a was 3. Now, if our a was less than 1, so if we were to set a value of 0.5 for the coefficient here, it would shrink everything down. And so now, instead of being at 1, this right here is at 0.5. And this is -0.5. But the key features line up the same. So when we're talking about sine or cosine, they're all going to have an amplitude. And essentially that amplitude is the hypotenuse of the theoretical triangle we're making. So we talked about before that the unit circle all had a hypotenuse of 1 or a radius of 1. And by multiplying by an a here, you can essentially have larger or smaller circles. And the different size of these circles is going to determine how much the range is either stretched or compressed. So if you have values less than 1, then our similar triangles that we were making are going to actually be smaller versions. So instead of the hypotenuse being 1, it's going to be 0.5. Um, if we multiplied by 3 like we did over here, then what ends up happening is we essentially have a hypotenuse of 3, and the whole circle gets stretched to 3 times as large, to a radius of 3, and each of the points represents a triangle with a hypotenuse of radius 3. And that's what essentially we did last or 2 classes ago when we talked about finding trig values at any angle, is we worried about the scale essentially. So amplitude deals with the scale. Now, the other thing we want to talk about is the period. So when we're talking about the period, that's how long it takes us to get around the unit circle. So in all the previous examples, we started at 0, and then we went to pi over 2 or 90. Then we went to pi, and then we went to 3 pi over 2, and then we went back to 2 pi. So 0 slash 2 pi. So this is if you're going around the circle at a standard pace. Not every trig function has the same period. So the period is the amount of time, or in this case, the amount of angle that we have to rotate in order to complete the circle. So we can actually go through the circle faster or slower. And to change that, we end up looking at the coefficient of x here, b. So if we wanted to look at changes in period, y equals a sine of bx. So the standard period, again, for a circle is 2 pi. So if we wanted to modify the period, what we do is we actually use the following. So the period equals 2 pi over b. So essentially, if we have a large b, something bigger than 1, what's going to happen is that our denominator here is going to be larger and our period is going to be smaller overall, which means that we're going to get through our full cycle faster. So for example, if b was 2, y equals a times sine of 2x. What ends up happening is we reach our features twice as fast. So our x value to reach, so again, our key features are 0, pi over 2, pi, 3 pi over 2, and 2 pi. So we're going to actually get to these twice as fast. So in order to get to pi over 2, so we say pi over 2 equals 2 times x. What we ended up getting is that our x value to get pi over 2 is going to be pi over 4. So at pi over 4, we're going to be at 1. When we solve for pi here, we're going to get pi over 2. So we're going to complete our period twice as fast, which means we're going to have twice as many oscillations or cycles in the same amount of time. So our normal time is from 0 to 2 pi, but instead of completing one cycle, we actually complete a full cycle all the way by pi, and then we complete a second cycle by 2 pi. So instead of our key features being at pi over 2, they're at pi over 4, at pi over 2, at 3 pi over 4, and at pi, because essentially anytime we plug in these values, we're going to multiply them by 2, and so pi over 4 becomes pi over 2. Pi over 2 becomes pi, 3 pi over 4 becomes 3 pi over 2, and pi becomes 2 pi. So we go through the full cycle that much faster. Now, if we were to have a value that's smaller than 1, so let's say zero 0.5, now to find our key features, we're going to say, oh, well, pi over 2 equals 1/2 x. And so we multiply both sides by 2 and we get x equals pi. So that means for the first key feature, it's not going to happen at pi over 2 or pi over 4 as it did over here. It's actually going to happen at pi. So essentially, we've stretched out the graph horizontally. We will have key features at pi, 2 pi, 3 pi, and 4 pi. And that's the amount of time it takes to complete one cycle here. And again, the reason being is because we're going through our indexes either faster or slower. So imagine our x values or our thetas are the index or the place that we're trying to find compared to the original sine function or cosine function. So again, the key features for the original sine are 0, pi over 2, pi, 3 pi over 2, and 2 pi. But when we translate these, when we stretch them or compress them horizontally, we're going to plug in different x values to get those key features. So whatever our b value is, so y equals a times the cosine of bx, this b is essentially going to determine how quickly we get through our circle. So if b is small, then what's going to happen is, and when I say small, less than 1. So if b is less than 1, it's actually going to take bigger x's to get all the way to 2 pi to complete the full cycle. If our b is greater than 1, then we're going to get through it faster, and this is going to compress the graph like it did over here. And the reason being is because every x value we plug in, since we're multiplying it by b, we're going to reach where bx equals our key features, we're going to reach them faster. So if our key features are at 0, pi over 2, pi, 3 pi over 2, and 2 pi, if our b value is 6, then what we're going to get, so we're going to get 6x equals, let's just pick one, we'll say 3 pi over 2. So to get to this feature, we end up dividing both sides by 6, and we end up getting 3 pi over 12, or 1/4 pi, so pi over 4. So that means we're going 3/4 the way around the circle at pi over 4 instead of at 3 pi over 2. So that multiplier by b determines how fast we get through the cycle, and the bigger that value of b is, the quicker we go through the cycle and the closer together our waves are. And the smaller the value of b, the longer it takes to complete one cycle. So we're going to stretch out those sine and cosine functions. In addition to our normal stretching and compressing both vertically and horizontally, again, amplitude is the vertical stretching and compressing, and period, or changes in period, are your horizontal stretches and compressions. The other thing we've done with graphs in the past have been translations. So typically, we can translate a function by adding to the x, or we can add or subtract from the y. If I wanted to have y equals, again, sine of x, and I wanted to shift it up 2, I'd add to the total thing. I'd say plus 2. And when I do that, what's going to happen is the whole graph is going to shift vertically up 2. If we wanted to shift it down, we'd subtract from the total function. If we wanted to shift left or right, it's a little bit different. So instead of adding or subtracting to the total, what we'd do is we'd say like y equals sine of x. If we wanted to shift, we'd say like minus pi. And this would shift the whole thing over pi. So our normal graph, we started at 0, and then we went to 1 at pi over 2, 0 at pi, -1 at 3 pi over 2, and 0 at 2 pi. So if we shifted it over pi, the whole graph, instead of starting here and going up and then down and then back up, we're actually starting at -pi. So when we plug in -pi, that gives me 0. So at -pi, we're then starting our period. And so halfway, instead of being at pi, halfway is now at 0. And all the way, instead of being at 2 pi, is now at pi. So this shifts everything. So let's say we added pi over 2. So again, if we were to graph y equals sine of x plus pi over 2, this would shift it by pi over 2. And if you notice, this graph right here is actually identical to our graph of cosine, because cosine is the same graph as sine, just shifted over by pi over 2. So sine of x minus 3 pi over 2 is equal to the sine of x plus pi over 2, and it's also equal to the cosine of x. So this commonality and how similar sine and cosine are is the reason why trig ends up being complicated. And what I mean by that is solving trig problems, there's a lot more ways of solving them because you can transform them from one trig function into another without actually changing the values. They're so similar that you end up having a lot of options, and these options can sometimes make things seem more difficult. There is no direct, easy path that you can always do. Now, one of the other things I want to show you is a combination of a bunch of different things. So let's say that we took the amplitude and we multiplied it by 4, and we changed the period so that it would happen 3 times as fast. And let's say that we had a shift vertically of -2. Let's say that we had no horizontal shift. So again, let me write the equation here. So the equation here would be y equals 4 times the sine of 3x minus 2. And so let's talk about what each of these things does individually. So this 4 stretches the graph. So the distance between our middle, which is this line right here, and our peaks and valleys. So this height right here, or if we looked at it down here, from here to here. So this height is 4. So that is the amplitude. Now notice that we multiplied with a b of 3. So that means in 2 pi, we're going to actually go through the cycles 3 times as fast. So we're going to have, starting here, our first completion is here. Then we complete the second cycle here, and we complete the third cycle here at 2 pi. So 2 pi is what it would normally do, but we're doing it 3 times as fast. So we're going to do 3 oscillations in that same amount of time. So up, down, back, up, down, back, up, down, back. So we've done that 3 times in 2 pi. Finally, this right here is our vertical shift. So we've shifted the whole graph down 2. So instead of being centered on the x-axis, we are now centering at -2, which is what this line is. And our graph is going to go all the way up to +2, and it's going to go down to -6. So these points are all -6, and these points are all +2. And we can modify a bunch of different things. So if we look at the base function, so we'll look at it for cosine. So if y equals a times the cosine of bx minus c plus d. Again, our a is our amplitude. It's our stretch vertically. So if a is bigger than 1, we're stretching. If a is less than 1, we're compressing. Our b is our horizontal stretch or compression. So if b is bigger than 1, then we're going to be compressing horizontally because we're going to be cycling through the unit circle faster. If our b is less than 1, then it's going to be stretched out and it's going to take longer to complete each cycle. So if we had, instead of this being 3x, if we had it 1/3, then instead of finishing at 2 pi, we'd finish at 6 pi. Now this c is again any horizontal shifts. So this is where we translate all of our points either left or right. And because it's a repeated pattern, aka a period, when we have these horizontal shifts, it doesn't actually look like it's changing the function that much. So if we have a shift of, so if we were to subtract 6 pi, well, we actually aren't shifting the graph at all because the pattern repeats over and over and over again, we're going to be at the same spot. Because again, if we look at our unit circle, we start at 0. Negative 6 pi would mean we would go negative 2 pi, negative 4 pi, negative 6 pi, and we're at the same spot on the unit circle. So realistically, our shifts, essentially every shift can be reflected by a smaller shift that's between 0 and 2 pi. And then finally, our D is just a vertical shift like we've done with everything algebraically. Now, these same shifts we've done before for other functions, not just trig functions. So if you recall in the beginning of the year, a quadratic function or a parabola, it had a vertex. So depending upon where this vertex was, that was changed by vertical and horizontal shifts. So let's say that we moved it up 2 and over 1. So now instead of being at 0, 0 like it is here, our point would actually be at 1 comma 2. So our whole thing would shift up and to the right. If we wanted a vertical stretch, we multiplied by the x squared function. So by the quadratic function, we had a constant multiplier, and that would cause it to stretch or shrink. And we could do it both horizontally and vertically. The same thing happens with lines. So if you look at any line, y equals mx plus b, this m is our stretch or compression. So if our m is 1, we have a nice identity function. The b will shift it up or left or right. And because it's a first degree, a shift up is also a shift left. A shift down is also a shift right. And so there is no separate C and D like there is for the trig function here. And the same thing with the vertical and horizontal stretching. So if we're to stretch it vertically, meaning have a steeper slope, that's also a horizontal compression. If we were to have a shallower slope, that's a horizontal stretch. We're taking points that were here and we're moving them further away horizontally, but we're also moving them closer vertically. So if we look at this point compared to this point, the distance here, the amount up and the amount over, compared to over here, the amount up is smaller than the amount over because we've had a horizontal stretch making the amount over bigger, and we've had a vertical compression making the amount up smaller. And the same goes for the steeper slope. So when we have a steeper slope, our vertical gets stretched and our horizontal gets compressed. So we've looked at these same transformations before, just not for trig functions. And they work the exact same way as they do for non-trig functions. These are general for any function if we want to do transformations. So for example, if we had a negative for our a, that would be a reflection around the x-axis, or in this case, around whatever our vertical shift is.